Hello, this is Dr. Todd Daniel, and for week 9, we are going to be talking about z-scores and z-tests. And so as this introduction to z-scores, we're going to begin by talking about the z-distribution, which is a normal curve. Now the z-score works like this. A z-score describes how far a raw score falls from the mean in standard deviation units. And already this gives us a hint as to what the z-score formula is going to be. It tells us how far a raw score is from the mean. So what do we do to find out how far one thing is from another? How far one number is from another? We're going to subtract. So we're going to subtract the mean from the raw score. And it's in standard deviation units. And that implies that we will be dividing by standard deviation. So more about that in a moment. First, let's take a look at these z-scores. What you see are 6 examples of z-scores. A z of a positive 1.32, or a z of a positive 0.01, or a z of negative 1.96, and so on. Now there are some things about these z-scores that you should notice that are common to all z-scores. First is this sign. The sign tells you whether the z-score is above or below the mean. The second is the number. It's the distance between the score and the mean in terms of standard deviation. This implies that a positive z-score will always be larger than the mean, and a score at the mean has a z equal to 0. So let's review these concepts. You should always include the positive or negative sign with your z-score. And, of course, you should have a number. That number should be rounded to 2 decimal places, even if the second number would be a 0. And third, we should include a leading 0 if the z-score is less than 1. So let's review to see what is right and wrong about these examples. In the first example, with a 1.23, what's wrong? Did not include a positive sign. What's wrong with the second example? Didn't include that leading 0. And what's wrong with the third example? Didn't round to 2 decimal places. So notice the pattern for this z-score. You will be using this pattern for all examples of z-scores that you will be writing. Now there are 3 things that we can do with z-scores. Most commonly, z-scores are used for comparing scores from different distributions. So let's say that you and your friend both take tests for getting into college. You take the SAT and your friend takes the ACT. You get a 30 on the ACT, your friend gets a 650 on the ACT. Which of those scores is higher? Well, 650 is certainly more than 30, well, quite a bit more than 30, so that must be better, right? The only way to know for sure is to standardize those scores so that they can be easily compared. And we can do that using z-scores. A second use for z-scores is for computing the relative frequency of scores from any distribution. And that's where we create a z-score, and that gives us an indication of how far the score falls from the mean. And this could be very useful in a number of ways. We'll be using that a little bit later. And finally, a third use for the z-score is for hypothesis testing, for interpreting sample means, how far a sample mean falls from the population mean in standard deviation units. And that is called a z-test. So let's talk about what's called the z-distribution. A z-distribution results after transforming any distribution of raw scores into z-scores. And like this bundt pan, which can turn any kind of cake mix into something shaped like a bundt pan, the z-distribution transformation can turn any distribution of raw scores into something shaped like z-scores. Now this is not the same as saying that it will make them into a normal curve, but it will make them something that is comparable between other standardized z-distributions. Now the z-distribution itself, the larger z distribution, is always in the shape of a normal curve. If you transform a non-normal distribution into z-scores, it doesn't change that distribution into a normal curve. But we're going to start with a simple example using z-scores in the shape of a normal curve. Second, the z distribution always has a mean of 0 and a standard deviation of 1. This is going to be very, very useful to us, as one z-score is going to equal 1 standard deviation. Any z-score that exceeds positive or negative 1.96 will be considered statistically significant. That means that it is significantly different, and that is going to be important when we talk about z-tests. The larger the z-score, the larger the value of the raw score. So as we get further and further above the mean, the z-score increases, as does the raw score underlying it. And in a normal distribution, z-scores are seldom greater than plus or minus 3 standard deviations. We're going to see some examples where we can get z-scores greater than 3, but they are so microscopically unlikely that we're going to conclude they're representing a different population. 99+% of your z-scores are going to be within 3 standard deviations. So it's very unlikely that you'll get a z-score greater than positive 3 or less than negative 3 through random chance. And this leads us then to the z-score formula. This is what we're going to be using in our next video. So here are the parts of the z formula. It's z equals x minus mu divided by sigma, where x is the raw score, mu is the population mean, and sigma is the population standard deviation. So a z-score tells us how far a raw score, x, falls from the mean, mu, in standard deviation units, sigma. And that is the z-score formula. Let's find out how we will use this formula.